We've spoken about a bit about quantum physics, spoke about the Higgs boson as well. Let's try to go even deeper.
All right.
Let's try to go even smaller with string theory. What is string theory?
Yeah. So string theory has, again, a long history, which we can go into if you'd like.
Sure.
Well, it originated in attempts actually to explain what we were just discussing, to explain the structure of particles that were being discovered by particle accelerators back then. And what it looked like is you had a series of particles which behaved as though they were connected by a sort of a stretchy elastic string. So as if you had two heavy particles connected by a string, and those particles could they could rotate around each other, and that would give them some extra angular momentum, some extra spin, and also some extra energy. So two heavy particles connected by a string with some elasticity to it. So they can rotate, they can spin. You can imagine two heavy balls connected by a rope. You could throw it up in the air with some spin, and it'll rotate. And this being quantum mechanics, the amounts of rotation are quantized. So the allowed angular momentum of that system is quantized. It can't be anything. It has certain discrete values.
Mm-hmm.
And also the mass, the energy associated with those motions, it corresponds to the angular momentum in a particular way.
Okay.
And that fit the pattern that was being observed back then. What we now understand is that it's not literally a fundamental string which is responsible for those patterns. It's rather what's called the strong force, the force that binds protons and quarks and neutrons together into atomic nuclei. And that force does act in many respects like a string.
Mm-hmm.
And that's why they were seeing those patterns back then. So that's how it started. But when people started to investigate what would be the consequences of a theory like this, where there's a string-like objects, they uncovered a fascinating mathematical structure. And physicists are always intrigued when they come across something like that, something very rich and complex. We have a tendency to think, if this exists, if this structure is there, it's probably used for something in nature. That doesn't always turn out to be the case, but whether it's the case for string theory, we still don't know for sure. But anyway, people got really interested in that and studied it, delved very deep into it. And they discovered that string theories have certain features that really do make them look a bit like the physical world. Probably the most interesting is that they contain a massless spin-2 particle. So I mentioned before that if the force of gravity is mediated by a particle, it has spin-2. Mm-hmm. And it would be a massless spin-2 particle. And string theory always contains a massless spin-2 particle. Now, this was really interesting because string theory is a quantum theory. We understand how to make it a quantum theory. But prior to the existence of string theory and the realization that it contained this so-called graviton, no one knew how to quantize gravity. And to date, string theory is really the only way to quantize gravity that appears to make sense. There's been lots of attempts to do it in other ways. A little bit of progress has been made, but not much. I think it's safe to say that string theory is the only quantum theory of gravity that we have to date. So does that mean it's correct? No, but if you're interested in how to understand gravity at the quantum level, it's really your only the only bet that you have, the only theory you have where you can study that. And understanding gravity at the quantum level is a really fascinating thing. So questions about Hawking radiation, for instance, that's when black holes are not actually black but radiate. Questions about the origins of the universe, the Big Bang, multiverse, these sorts of questions mostly, to get into them deeply, necessitate a quantum theory of gravity. And so people have been studying string theory with a lot of excitement since then. And like I said, to date, we don't know for sure that it's the right theory. So one of the strange things about string theory that is probably the most hard to understand is the fact that it doesn't make sense in 3+1 space-time dimensions, 3 space and 1 time. So the versions of string theory that we understand make sense only in 9 space and 1 time dimension. And then you may ask, where are the other 6? And what we've learned is that theories that contain gravity in the form that I mentioned, that have a massless spin-2 particle. So those are theories that look like what Einstein predicted gravity should look like back in around 1916 or so. Einstein's theory says that space and time are dynamical. They're not rigid, fixed structures. Mm-hmm. And the geometry of space, which sounds like an odd thing to say, but it's a concept that makes sense, is something which changes with time. There's a set of equations, differential equations, which govern how space evolves over time. So Einstein was able to explain gravity that way by space-time curvature. So in a theory that has extra spatial dimensions, if you want to explain why we only observe 3, what you need to do is say that the other 6 are compactified. That's a little bit familiar to people who played old arcade games like Asteroids.
Yeah.
Where if something goes off the screen on the right, it pops up again on the left, or it goes off the screen on the top, it pops up on the bottom. Yeah. So if you think about it for a little bit, you realize that two-dimensional screen is actually the surface of a bagel or a donut. It's a torus. There's 2 cycles. You can go around one way or the other way, just like you can wrap around the bagel the short way or the long way. If you're stuck on the surface of the bagel, it's like being in that game of Asteroids. So that's an example of compactifying directions.
Is the Calabi-Yau manifold also a subset of the compactification?
Yeah. Okay. Yeah. So Calabi-Yaus are manifolds that have certain special mathematical properties that make them very interesting candidates for what these 6 dimensions could look like. But the simple version is just you put what are called periodic boundary conditions, like in the game of Asteroids, on those 6 dimensions. And as long as the distance you have to go before you come back to where you started is sufficiently short, you won't be able to tell, you as a much larger observer won't be able to tell that dimension is even there. So it's probably a little bit hard to wrap your head around, but yeah, I'm trying to think if there's one way to think about it is that if you are going to come back to where you started when you wrap around this direction and go a certain distance in this direction, then either the quantity you're talking about doesn't depend on that direction at all. Either it's constant, in which case, of course, it can exist in that space, or it does depend on that direction. But if it does depend on it, it has to vary pretty rapidly. It has to change rapidly enough that whatever change it goes through is complete by the time you come back to where you started. So as you make this distance shorter and shorter, you're asking for anything that isn't constant to become extremely rapidly varying. And in quantum mechanics, to have something that varies very rapidly always corresponds to a lot of energy. So if you had really like an electron probability cloud, let's say, around a proton, and you want to say that probability cloud depends on this compact direction, it's different at different points on the compact direction, but it makes sense. So it comes back to its same value it had when you go once around. Then that probability cloud has to be a function which varies really rapidly over a very short distance. It goes through a full cycle of variation. And again, in quantum mechanics, that means a lot of energy. So if you did have a probability cloud like that, it would correspond to an extremely energetic state. And that's why we don't see it when the direction has a very short distance associated to it, because anything that depends on that direction would be extremely energetic, and we wouldn't be able to produce it in a particle accelerator, and we certainly wouldn't see it in our everyday world. So bottom line, at low energies, nothing depends on these extra 6 dimensions. Everything is completely uniform and constant with respect to those directions and depends only on the other 3. And so our experience is as 3-dimensional observers.